All right. So if you don't see this table on the left, just let me know. I'm sharing a table with two columns, size in square meters, and the column on the right is the selling price in millions. And I'll tell you what this data is all about. Okay. So what you have is, what you're given is two columns of data. And what you want to do is you want to use one of those columns to predict the second column. Now, in the real world, this is very often used. It's a very powerful tool. It's a statistics model. What we're trying to do is we're trying to create a model that if you give it the size in terms of square meterage, we want to predict what the selling price of that house would be. So that's what the second column is. So for instance, in the first row, we're saying for square meter size of 85, we expect the selling price to be 1.2 million rands. And for the next row, for a slightly bigger size, 110, we expect the size to be the selling price to be 1.5 million. So if we had to plot this, okay, so I'm going to make this column, the first column, my X column. And I'm not just doing it by randomly doing it. There's a reason why I'm doing this, is because I expect the size to influence the selling price and not the other way around. And it's very important that you identify that and you know that, okay? Because that will determine what you're using to predict the other variable. And in terms of using your calculator, it's going to be very important because your calculator doesn't really have columns for size and selling price. It just has X and Y. And you need to tell it what is the X and Y. So the X, or the size, is our independent variable. Okay, that's our independent variable. And the reason being is because the size isn't affected by anything, so it's independent. But based on the size, it influences the selling price. So this is the dependent variable, because it depends on the size, or in other words, the X, right? It's very important you identify which is your dependent and independent. Your independent will always be X, and your dependent will be Y. So if I had to plot this, and I'm going to do a rough plot, and you're welcome to plot this to scale when you have some time. You don't have to do it now. Okay, so here is our X-axis and our Y-axis. And what we would have on the Y-axis would be the selling price. So here, selling price. And here we would have the size. Sorry, size. All right, so if I plot the first point and say I did this to scale, so the first X value is 85. If you look at this row here, it's 85. So let's say 85 is there. The selling price is 1.2, so say it's around there. Then that's the first point. Okay, the next point will be 110 and 1.5. So we just put dots for each of these points. There's 10 data points. There's 10 rows of data. If I had to do it, it'll be something like this. Okay, it's not accurate, but you more or less get the point. Now you can see from all these data points, what it's telling you is as size increases, so as you move to the right, what's happening is that your Y value is increasing. So the selling price is increasing. And that is what you would expect for a real world kind of problem. Okay, the more area you have for the house, okay, the more land, you expect the price to be higher, right? So this is an example of what we would call positively correlated data. And all that means is that when your X variable increases, your Y variable also increases. So that's what positively correlated data is. You can have data that is negatively correlated. Let me give you an example, all right? I'm sure pretty much all of us can associate with this. If we ever bought a car, or if we plan to buy a car, you'll know that if you're buying a second-hand car, the higher the mileage, so let's put mileage on the X-axis. If you have more mileage on that vehicle, you expect the price to be lower. So if I had the price of the vehicle here, then what happens is as I increase the mileage, the price is going to move down. So the data I would expect to look like this. It'll be sloping the other way. So this is an example of negatively correlated data. Correlated. And then this is an example of positively correlated data. Okay, because as you increase the x, the y increases. And for negatively correlated, when you increase the x, your y actually decreases. Can anyone give me an example of negatively correlated data? I gave you one, which is price and mileage. Can anyone think of another example off the bat? Just checking. Just apply your minds to it. There must be something that you can think of that as you increase something, it would cause the other variable to decrease. Anything else? What else would affect the price of a vehicle? Think about it. If you bought a vehicle, if you bought a new vehicle, that is a model that was built in 2026, you expect the price to be higher. But if you bought an older model, then you expect the price to be lower. So age of a vehicle, okay? As you increase the age of a vehicle, the price will decrease. Okay, I'm hoping you kind of get the idea. But if you do think of an example, please just drop it in the chat. Okay, apply your minds to it, because you will be assessed in this, for your next assignment and your exam. So probably best to give it a try now. All right, so let's get back to the whiteboard. Okay, so you understand positively correlated data, and that's the example we're doing right now, which is the selling price of the house and the size of the land. Okay, so let's continue with this example. All right. So I'm just going to clear this out. This clears everything out. Cool. All right. Now, let's get back to this problem. What we want to do is, okay, we have this data, and we know that it kind of follows this shape. All right. And what we're trying to do is we're trying to fit a line. So we want to fit a line to this data. Now, some of you may ask, okay, what do we mean by fit a line? Okay, now some of you may recall from high school maths. It's not important that if you don't. If you have any line, a line is given by a specific equation, and that equation is y equals mx plus c. Some books write it as bx plus a. Doesn't really matter. Okay, it's just letters. But all it basically tells you is that this a in the equation, or the c in the equation, it tells you where this line cuts the y-axis. Okay, here. That's what that a and the c tells you. And the m or the b tells you the slope of the line. Now, what do I mean by slope? Okay, so basically, let's say we have this line here. The slope of this line could be m equals 2. But the slope of this line, you can see it's less steep. So it'll have a lower slope. So the m would be, let's say, 1. This line has an even less steep slope. It's more gradual. So the m decreases. Let's say it's a half. That's what your m tells you. Your m tells you how steep the slope is. And if you have those two measures, if you have your intercept and you have your slope, then that's all you need to kind of characterize the line and to use it to get values from it. Okay, so that's what we need to try and figure out. We need to figure out what line would best represent those data points above. Okay, and what do I mean by best represent? Well, what we're trying to say is what line would basically overlap all those dots as best as possible, or be as close to the dots as possible. And we want that line to be close to the dots because we are going to use that line to make predictions. And if that line is very far away from the dots, then our predictions are going to be very far away from what is actually happening. So for instance, let's say, let me use a different color, right? If I had to use this line, this green line, I wouldn't want this green line to represent the data points because it's so far away from the data points. You can see that it's quite far away. So if I use this line to kind of make predictions to the actual data points, the blue dots, it's going to be very far off. Okay, it's going to be very inaccurate. So I want a line that is as close as possible to those dots. And to kind of characterize the line, all I need to define that line is the slope, in other words, the M and the C, or the A and the B. So I'm going to use A and B just because your formula sheet uses A and B. Okay, so I don't want to confuse you, but generally the equation of a line is given by mx plus c, but we are going to use the B and the A instead. And also because your calculator uses the A and the B. So what are we going to do with this equation? Well, we're going to determine what these values are, A and B, and then we're going to make predictions with it. All right, so that's where we're going to use our calculator. So get your calculator out. Okay, then you're going to switch it on. And the first thing you basically want to do is you want to activate the regression function. Okay, and that's the function that has a plus bx, the same equation of a line. And how we do that? Okay, you're going to press mode. You press mode. So first step, press mode. Then you're going to press stat2. And then you'll see the option here, a plus bx. You should see it. Everyone should see it. It should be option 2, but if it's another number, just press that number. So if it's option 2, press 2. And everyone should see a column that has x, y, and frequency. And we don't need to worry about the frequency too much. You can ignore that. But the x and the y is where you're going to capture this data. So this, remember what I said earlier, this is your x column and this is your y column. Okay, so you are going to capture the data just like how we did last week. All right, you enter the numbers and you hit equals to. So for the first value for x, you're going to capture 85 and hit equals to. The next value is 110 and hit equals to, etc., all the way to the last value, which is 350. Then do the same thing for the y column. Okay, do that now, please. All the way to the last y column, 4.9. Remember to capture the data, you just press equal to. Okay, so I'll give you a minute. Please capture the data because you're gonna have to use this data to get the values that we need for this lesson. Okay, let's check if there's any questions. Okay, I'm hoping everyone captured the data. All right, so once you've captured the data, once you captured all of it, you can press AC, right, on your calculator. All right, now what we're going to do is we're going to get the gradient first. We're going to get the value B first. Okay, what is that value? All right, so what is the slope. And how we get that? Okay, so what you're going to press first is you're going to press Shift. Okay, then you're going to press 1. Press the button 1. And you should see an option that says REG, regression. Okay. Select that option. If it's option 5, you're going to press that. And there you will see B. It should be option 2 because we want that value. That's going to be our slope. Okay, you select that. Everyone should have a value. If you capture the numbers correctly, you should get a value of B being 0.0139. Okay. Okay, now let's do the same thing to get the intercept, or in other words, A. So it's the same process, exactly the same process, except here it'll be A, and it should be option 1. Follow the same step. And everyone should get a value of A being minus 0.0157. You can round to 2 decimals, it's fine. I'm just rounding to, but more to be more accurate. But 2 decimals is the minimum. Okay. Let's check if there's any questions. Okay, I'm hoping everything's okay, but just shout if there's any questions. All right, so you've got your A and B, and now what you need to do is write out the equation. Okay, so you've done the hard part. Let's just give me a second. Okay, almost done. All right, cool. So what we just need to do is write out the equation. We have our A, we have our B, and this is the equation. A plus bx. So we're going to write out y equals A, but instead of A, we're going to write what the value of A is. It's minus 0.0157. Zero 157 plus B, which is this value, x. That's the equation. Now we don't usually write y. It's just a technical thing. We generally write y hat. And why we write y hat is because y is the actual values, but the y hat is just predictions. We're going to use this equation to make predictions. So let's do an example. All right, let's say if you look at the data, right, we have a house that's 110 square meter size, and then we have a house of 150. But we don't have a house that's 125 in size. So what price should we assign that? And that's where this equation comes in. It helps us make those estimates. So in other words, if I want to estimate the sale price for a house where the size is 125 square meters, all I do is I plug this 125 into the equation and I'll get the estimated sales price. And if I do that, right, you can give it a shot. If you plug in 125, then the estimated sales price will be 1.7 million. So your estimated sales price is 1.7 million. Right? Or in other words, instead of writing mil, you can write the full value 1700. That's what you estimate the price to be. That's what's so handy about this equation. Okay, you can make estimated sales prices for any given size, right? That's the usefulness or the power of this of regression. So as a quiz, let's say I want to estimate the sales price for a house. So the quiz in now, what is the estimated sales price for a house of size 270? What is the estimated sales price? There's your equation. Okay, is it option 1? Is it 2.9 million? Or is it option 2? Is it 3.7 million? How many of you say option 1 and how many of you say option 2? Okay, try that in your calculator. This is a very typical question that you will get asked. Like 99% certain you will get asked a question like this. Because that is, you've done all this work to create that equation, and what's the point of not using it? And this is showing you how to use it. See in the chat. Kelly, good question. Fuel consumption, would it affect anything? Definitely, yeah. Good point. Good point. You'd expect vehicles that are heavier on fuel consumption to be, I wouldn't say like higher in price, probably less in demand. Or you could even use fuel consumption for mileage, right? The higher your fuel consumption, the less miles you can actually get on a vehicle. So if Y was the mileage that you can get with the vehicle, then your X would be the fuel consumption. As you increase fuel consumption, you'll get less miles traveling. Buying in bulk, yeah, that's a good one. That's actually a very good one. So the more stuff you buy in bulk, the bigger your savings. So that will be okay, positively correlated. Oh, wait, I guess what you're saying. The more items you buy in bulk, the lower the price. So those are inversely correlated. It's a good example. Yeah. So the price versus buying in bulk. The more stuff you buy in bulk, the lower the price. Good examples. Anyone? No one gave it a shot. No one gave it a try. What options do you? If you have a house that's 270 square meters, what is the estimated sales price? I can't be the only one that's actually trying to do this. Come on, give it a shot. I wrote the equation up for you. All you got to do is plug in the value into it and get the estimated sales price. Oh, nice, Neil. Okay, good. Very good. Yeah, it's 3.7. Okay, I'm just assuming that everyone understands how to work this out. All right, but please let me know otherwise. All right, so what I've done now is I've showed you how to work out A and B, okay, the values for the equation. Now I've shown you the shortcut method. All right, it's very quick and easy to do that with your calculator. But I do need to show you how to do it the long way, and that's because you will get tested on the long way. So what I would advise you is if the question only awards 2 marks and less, then do it the way we just did it now. Just pull the values from your calculator. But if the question awards 3 marks or more, then you have to do it using the long method. Okay, now what is the long method? The long method means using the equations, which is it's given to you, so don't worry about trying to memorize it. Okay, don't panic when you see the equations that I'm going to write down now. It's in your formula sheet. Okay, it's just important that you know how to use it. So the equations to actually find the slope is b equals n sum xy minus sum x sum y all over sum x squared. Sorry, n times sum x squared minus sum x squared. All right, so yeah, I know it's a lot of stuff in this equation, but your calculator will actually do a lot of the work for you. So let me draw your attention to the first term here, the n. All right, the n, you can either use your calculator to determine it, or just count the number of rows in your table. Now, if you count the number of rows in your table, you'll see there's just 10 rows. So that's your n. Okay, it's just the number of rows in your table. The next term is this here, the sum xy. Now, if you want that value, all you got to do in your calculator, okay, you'll press Shift, okay, then you're going to press 1, and then you'll see the option that says sum, because that's what this value is. It's the sum of x times y. You're going to select the option that says sum. And if you do that, you'll see this option there. You'll see that, and you just select which option it is. On my calculator, it's option 5. Right? And if you select that, option 5, you'll get this value. It equals to, and you will have the value. All right, so that should be 7, I think it's 7370. All right, so you do the same thing for every other item. Okay, you follow this process here. Shift, 1, sum, and select which one you want. So if you wanted sum x instead, you select that. If you wanted sum y, select that. Sum x squared, select that. It'll give you all the values for the equation, and all you do is you plug all these values into the equation, and you'll get the same answer we got earlier for b, which was b equals 0.0139. So this is the long method. Like I said, if the question is awarding 3 marks or more, do it the long way. But if it's 2 marks, you can do it the shortcut, which we did earlier. And you do need to know both. All right. Now I showed you the equation for b. Let me show you the equation for a. A is actually easier. And the reason I showed you b first is because you actually need b to work out a. So that's your b, equation for b. The equation for a is sum y minus b times sum x all over n. So it's a less busy equation. Like I said, you need b first to get a. All right, and you do it the same way that I showed you how to do a. Find the values for sum y, sum x, and plug it into the equation. All right, that's the long method. Any questions? Yes, it is being recorded. I actually remembered this time, so thank you. All right. Okay. Well, next point. All right, so I showed you how to find the equation of the line. All right. Now, what I need to point out here, okay, and it's actually very important. When you found the equation of the line, all right, you would have had, we wrote it out earlier, we have y hat equals a, and our a was minus 0.0157 plus b, which is 0.0139x. That's the equation. Okay. Now, if you look at our data, okay, here, the x values go from 85 all the way to 350. So if I had to, let's say, sketch this graph again, that's our x-axis, that's our y-axis. Okay, so here we have size, and here we have selling price. All right, now the highest x value we got is 350, and the lowest x value we got is 85. So the lowest point we have here is 85. So let's say 85 is there. So that means our data only goes up to here, stops there. So I'll draw a vertical line up here, here. Our data stays within these boundaries. So our line was constructed within these x values. So why I'm drawing your attention to this is because we estimate this line between these x values. So we can only apply it between these x values. We generally don't apply it to values of x outside of that region. So for instance, if we had an x value where the size of the house was 400 square meters, so say your x value now is 400 square meters, it wouldn't be a reliable result to use this equation. And the reason being is because we know our data between these two values of x. We can see it, we can plot it, and we can see it, and we can tell that a straight line is a reasonable fit to this data. However, after that, we don't know how the data could be. It could be going this way. So in other words, it's almost like curving upwards. So if we had to use the line to make predictions, we are going to be very far off the mark. You can see this is where the actual values are. But if we're using the line, we are going to underpredict everything. So we use the line to make predictions for the x values we are given. So in other words, what we would say after we write the equation, we would say this equation is only valid for x values between 85 and 350. Now, this is how we write it mathematically. You don't have to, if you find this confusing, you don't have to do that. You can just state it in words. You can say for x between 85 and 350. That's good enough. But you can write it in the mathematical form if you want, but you have those options. But you should state that. You must state that after you write the equation, okay? Please remember that. After you write the equation, write either this or this. You've got to state where this equation is valid, all right? Okay, so I hope you understand that, but let me know otherwise.
Let me know otherwise. I have a question. So if we were given a value that is out of bounds in a test, like how would we answer that? Like would we say that we cannot predict it as this value is out of bound, or what would we say?
Okay, very good question. That's a good question. Generally, we wouldn't give you that, but it's not to say it's not possible at all. Answer the question. So we'll go back here and let me do this, right? So let's say we had this x value, all right? And let's do it. Let's do the prediction. So we'll plot that, we'll plug in the x value into the equation. And you can do that with me if you want. So you get y hat equals minus 0.015 plus 0.0139 times 400. Okay, so we will write that value, which is 5. It's I'm going to round it, so it's 5.5 million. All right. Now we would answer it. We would show that we know how to use the equation to calculate it, but we would provide a statement and say, however, this, now I can give you the mathematical term. I'll write it, but you don't have to always say it. Okay, so I'll say this is what we call extrapolating. Right. Or in other words, okay, I'll come back to what extrapolating is in a second. Or you can write, however, this is not reliable. Instead of putting extrapolating, just put not reliable. Right, you can put that. Right, and you could leave it that. You don't have to justify it as long as you put this here. As long as you had that here, you don't even have to say why, because you already said that this equation is only valid for that. Okay, now what do I mean by extrapolating? Now there's two things, right? There's interpolating and there's extrapolating. Okay, interpolating means we are just making estimates within the bounds of that x. So for instance, I want to make a prediction here. That's interpolating because it's within the bounds of x. Okay, any prediction within the bounds of our data, the x values, we would be interpolating. But whenever you do predictions outside the bounds, then you are extrapolating. That's what we mean by that. Okay, so I know this sounds like a fancy math term, but that's pretty much what it means. Okay, so this regression It's not reliable for extrapolating. It's reliable for interpolating. Or if you're not comfortable using those words, just say it's not reliable because the data point of 400 square meters is outside the domain or outside the range of X. Does that answer the question? Does it make sense?
Yes, that makes sense. Thank you.
No worries. Good question. All right. Okay, so we know how to do predictions. We know how to write the equation. All right, now I'm gonna draw your attention to something else, which is called correlation. Now, what do we mean by correlation? Now, correlation, we already discussed it earlier. Okay, remember, if your X increases and your Y increases, that means it's positively correlated. And then if your X increases but your Y decreases, then it's negatively correlated. And I gave you the example with the mileage of the car and the sales price. If you increase the mileage, the sales price drops. That's an example of negative correlation. But we can also determine the strength of the correlation. And the strength of the correlation is how, let me kind of explain this with data. So, all right. Let's say we could be measuring some X value here and some Y value. But if the data points are like this, now you can see that X is increasing, right? We're going to the right, X is increasing, but your Y isn't really changing. It's staying within these bounds. The Y isn't changing too much. So what this tells us is that your X doesn't really influence Y, because you can increase X, but your Y kind of just stays within this range. And this is an example of very weakly correlated data. So this is weakly correlated. All right. But then on the other hand, you can have data that where your X increases, as your X increases, you can clearly see that your Y is increasing. It's almost perfectly shaped. And if your line is very close to that data points, then it's not only positively correlated, it's also very strongly positively correlated.
Is there a difference between weak correlation and no correlation?
No, the same thing. The same thing. Weak correlation and no correlation is it's pretty much the same thing. The question you're asking is, we're going to work out how we measure correlation. There's actually a value we can assign to it. And if the value is close to 0, the symbol is actually R. If it's very close to 0, that means it's no correlation. If it's pretty small, and small is like less than 0.2, so say it's around 0.19, that's weakly correlated. So it just depends on the actual value. That's weakly, that is pretty much no correlation. That's the difference. It's actually the value itself. Make sense? I'll get to how we work out this R. We're coming there. I need to explain to you what it actually means before we actually do the calculation. All right, just let me know if there's, if there's more questions, if you didn't answer that. Happy to elaborate on that. Okay. All right, so now let's do another example. I did positively correlated, I did weakly correlated. Now let's do negatively correlated. So here, as you're increasing your X, your Y is decreasing, but you can still see that the line very closely aligns with the dots. So here, it may be negatively correlated, but it's strong because the line is very close to the points. So it's strong, negatively correlated. All right. And how do we actually determine the strength? Well, to your question, Danilo, we are going to use this value R. We're going to calculate this R. So everyone's got the data already in the calculator. All right. So the easy way to just get R is just pull it using your calculator. and you're going to use Shift, and you're going to press 1, and then you'll choose the option regression, REG, and everyone should see R after that. Okay, now select R. If it's your third option, select 3 and hit equals to, and write down in the chat what value you get. Okay, this is you to follow along, so I'm not going to do all the work here. You need to put the value down in the chat. I need to see that you're following. Cool. Cool, nice. That's it, yeah. I'm hoping everyone else gets the same value. You should get an R value of 0.998. Okay, now just so you know, R can take on the values. It can go as low as -1, and it can go as high as 1. That's the maximum it can go. All right. Now, don't worry about the sign for now, okay, the negative. Okay, I just want you to focus on the value. What you need to take away is that if your value is 0.8 and above, if it's 0.8 and above, then it's a very strong correlation. It's very strong. That's a very strong correlation. All right. Now, we got a positive value here. It's positive 0.998. So how you would interpret this is you would say it's a very strong positive correlation. That's how you would interpret it. Okay, because this 0.998, it's bigger than 0.8. So it classifies it as very strong. If you get a value from less than 0.8, so less than 0.8, but bigger than 0.6, 60%, then this is strong. This is a strong correlation. And anything below 0.6, you can say moderate, right? Weak is anything below 0.2. All right, just so you know. So I can write that out. Let me just let me just make some space here. Give me a second. Okay, so your ranges, just as a guideline, 0.8 and above. So R greater than 0.8, it's very strong. Okay, R between 0.6 and less than 0.8, we would say strong. Then above 0.2 and less than 0.6, we would say moderate. You could even say moderate to weak. And then less than 0.2, it's very weak. Very weak to no correlation. That's your ranges for R. Okay, you can use that as a guideline. Okay, that's how you determine what's strong, very strong. It depends on the R value you get. Now the difference, if it was negatively correlated, it makes no difference. All it means is that it's in a different direction. So for instance, if you had an R value of, let's say, minus 0.9, then how you would interpret that is, forget the negative for now, just look at the 0.9, and you can see that it's bigger than 0.8. So we would say it's a very strong negative correlation. Okay, make sure you understand how to interpret the correlation coefficient. Okay, the last thing I want to cover is something called the coefficient of determination. Okay, now it sounds like a lot, but it's very easy to actually calculate and interpret. Okay, so it's the coefficient of determination. And I'll explain what that is. So if you ever asked for this, all they're asking you to work out is r squared. Just take your r and square it and convert it to a percent. That's all you have to do. So in other words, everyone already worked out the r. I know you put in the chat the now, but everyone else, I'm hoping you gave it a shot. Your r was 0.998 if we round it. So all I'm going to do is going to take that value, 0.998. I'm going to square it, and I'm going to multiply it by 100%, just to make it a percent. That's all I'm going to do. And if you do that, you get an r squared value of 99.62%. All right, so the calculation is easy. And the interpretation, okay, what is r squared? It's a very useful statistic. Okay, it's used in the real world. And so it's important that you actually understand what this means. If ever you have to kind of interpret some statistical results, very often an r squared is going to be there for you to interpret. You want the r squared to be as high as possible. You want it to be close to 100%, right? And the reason being is your r squared tells you how good that x variable explains the y variable. In this problem, we're trying to see how size can be used to determine the selling price of the house. And if that r squared is high, the higher that r squared, then it tells us that size is very effective in explaining the selling price of the house. Okay. But how you would officially write this in the exam or assignment, okay, once you got this value, how you interpret it is the statement you would provide is you would say 99.62% of the variation of selling price, in other words, your y, can be explained by size. In other words, your x. That's how you interpret it. Now I'm going to emphasize this. I've seen a lot of students, instead of actually saying what the y is, they just put y. And instead of saying what the x is, they just put x. They don't say size for this example, and they don't say selling price. And if you do that, you won't get marked, okay? Because you're just providing the general interpretation. Okay, and that's not good enough. What we are trying to assess is that you can apply the theory in practice. So don't write y. You can write y in brackets if you want, but you must explicitly say what the y is. So here, like in my interpretation, I'm telling you that selling price is the y, and I'm also telling you that size is the x. All right, that's how you interpret it. So please make sure that you, whenever you're providing the interpretation, you must say what your x and your y is. Don't just leave it as x and y. Okay, that's what I wanted to cover today. Any questions? Anything that wasn't clear to you, you'd like me to go over? This is Learning Unit 4. The floor is yours. Or is everyone just too tired after the assignment? All right. Well, feel free to ask away, but great questions and thank you for joining. I will make the recording available as usual. And yeah, even if once you go over this video, if you still have any questions, please drop me an email. All right. Oh, and just to remind everyone, now you're welcome. I'm traveling for work next week. I will put an announcement out, so I won't have a synchronous session next week, but I will put a pre-recording of the contents. So please watch that. But I'll keep you posted via an announcement. Okay, so unfortunately, I have to travel next week, and so I won't have the live session. The live sessions, I do provide the links on the announcements, but there is a YouTube channel. Just let me put the channel. Hold on, I'm gonna stop sharing. I'll just put the link to the channel now in the chat. But the links are on ARC. Just give me a second. Playlist. No problem. But yeah, I do have it all listed on ARC. Maybe let me just share that. So when you're navigating on ARC, you can also find it. Okay, so go to ARC. You go to ARC. If you go to oops, I don't hear myself talk. I'm gonna go back to ARC. So here, let me know if you can't see it. Okay, I'm just gonna check. Yeah, you can. I'm sharing. So on the left, when you go to content, go to module information. If you scroll down, here, synchronous session recordings. There you go. We've had 3 so far. This will be, oh, actually I had the 4th one. Okay, yeah, I'll update this, but you have all the links here and the synchronous session recordings. Okay. All right. All right, everyone. Thanks for joining. Really appreciate it. We'll chat soon. No worries.